Good afternoon. I guess it is afternoon now. All right, so for those of you who haven't met me yet, I'm the Dean of Engineering, Cheryl Ehrman. I'd like to welcome everybody, and I'd like to welcome in particular any students or faculty colleagues from the College of Science to come. We're really always hoping we can bring audiences from different parts of campus when we have these. And today it's my pleasure to welcome Dr. Bruce Dunham. He is the Accelerator Director and is also the Associate Lab Director at the Stanford Linear Accelerator Center's National Accelerator Laboratory, or as I know it, SLAC, or as I also know it, that strange shaped thing as you drive up 280 towards San Francisco that I've been looking at all my life. So Dr. Dunham earned his master's in engineering management from the University of Wisconsin-Madison and his PhD in physics at the University of Illinois at Urbana-Champaign. Beginning in 1998, he worked for 8 years at GE Healthcare as its lead system designer and principal engineer. He then went on to serve for nearly 10 years as Director of Research and Development at Cornell University's Lab of Elementary Particle Physics. He joined the Stanford Linear Accelerator Center in 2016. I'm sure quite an improvement in the weather from all of those places that I mentioned. Working for 2 years as its Deputy Accelerator Director and now in his current role of Accelerator Director and Associate Lab Director for the last 10 months. In addition to his work and research, he also holds more than 20 US patents. So everyone, please help me to welcome Dr. Bruce Dunham.
Thanks. Okay, can you hear me okay? Yeah. All right, well, thanks for having me here. We're excited to come down and meet everybody. So I'm going to tell you a little bit about SLAC today. The first thing I want to get out of the way is we're not SLAC with a K. Every time I tell somebody I work at SLAC, they say, oh, when's the IPO going to be? And so I use SLAC all the time. I think it's great, but that's not us. So we're SLAC without the K. So anyway, I'll just give you a brief overview of what SLAC is. And we're part of the Department of Energy Lab System, which I'll tell you about, all the exciting things we're doing. But just to give you an idea where we are, so, whoops, sorry, this is 280. If you go down this way, it's towards you, San Jose. Up this way is San Francisco. Here's Sand Hill Road over here. SLAC is right here. Here's the 2-mile-long accelerator, so many times you've driven over this on your way to 280. All the venture capitalists, they all sit over here. Unfortunately, they don't give us much money, but we go over there and have lunch and hope we meet them. But so anyway, we're located in Menlo Park, and Stanford's just down here. So the Department of Energy has a national lab system. There's 17 national labs around the country. Lots of money, like $27 billion. We're in the Office of Science. That's really the largest funder of science in the country. So if you look where we are, so here's SLAC. There's quite a few labs. Lawrence Berkeley Lab is over here. It's a national lab. And Livermore has 2 branches here, so we have a big representation in the Bay Area. Again, there's one scattered all over the country. So SLAC has Office of Science Lab, and we're managed by Stanford, have over 1,500 employees. So it's a pretty big place, but you may or may not have heard of us before. So today you'll get to hear about all of the fun things we do. If anybody has questions during it, just raise your hand. That's fine. We can have questions now or later. But so SLAC is really part of Stanford. All the national labs have either university or some sort of consortium that manages them. So we're managed by Stanford. And so it's a great partnership. They provide a lot of things for us. We have over 400 acres of Stanford land, which is leased to the government for free. So Accelerator is part of that. There's lots of investment from Stanford back and forth. They help us with buildings, getting donors, all sorts of things. And of course, all the great professors and faculty at Stanford that we work with all the time. And also Stanford's a great partner for the Department of Energy. They trust them a lot, and they allow us to make our own contract for how we work with DOE, and that allows us to get rid of a lot of government regulations that cost a lot of money. So we can put more of our money into science and into just regulations and keeping track of things. So it's been quite a good partnership. There are a lot of joint institutes. So this is one way we work with Stanford, something called CIPAC, which is about understanding the universe. It's particle physics, astrophysics, cosmology. The Pulse Institute studies ultra-fast science of various kinds. Material science is a big thing, exploring interfaces, catalysis, batteries. And we have a recent one on biosciences and bioimaging. So those are just some of the ways we interact with Stanford. So anyway, SLAC started in 1962, believe it or not. Some Stanford professors, particle physics professors, wanted to do some new physics experiments. So they went to the local bar in Portola Valley called Alpine Inn, sat down, they started sketching out what they thought they wanted to build, and I don't know if this is actually what they sketched. This looks a little too nice for a napkin. But this is really what they came up with. So they sketched out this long accelerator. You see here, they have 280 drawn in here. It didn't exist at the time, but they assumed there was going to be something there. And so this is what they came up with. And so they convinced the government and Stanford to sign a contract. At the time, it cost $114 million to build this, which is a lot of money. And over there shows a picture of the accelerator. So the whole point of this was to do high energy physics and try to discover some of the new particles that people had predicted. And in fact, they got 3 Nobel Prizes out of all this for discovering the different quarks and filling out the particle table. So high energy physics was really the only thing that was going on at SLAC at that time. And this went through almost over 30 years into the 90s. And so when it got to the 90s, things started transitioning some. A lot of the high energy physics moved to Fermilab in Chicago, and now most of it's in Switzerland at CERN for Higgs studies. So a lot of the leadership in high energy physics has moved out of the US, unfortunately. But SLAC is still going strong, and so today I'll tell you about all the exciting things we're doing. So anyway, we've been repurposing SLAC's accelerator. The original thing that was built in 1962 is still running, and running very well. So we've, in fact, split it into different parts now. We've kind of split it into thirds. The whole thing's about 3 kilometers long, so we use different parts of the accelerator for different experiments. And what our main job at the moment is producing X-rays to use for experiments. So we have a national user facility. We produce an X-ray beam, an X-ray laser, which I'll tell you more about. And thousands of researchers from around the world come here to do experiments. They do them in chemistry, material science, biology, energy, just about anything they want. It's all free for anybody to use. They just have to come up with a proposal and use our beam lines. They can bring their own equipment. So it's really been very successful. And again, there are other national labs around the country that do similar things, but we're sort of the leaders in X-ray and ultra-fast science. So there are other things we still do. We still do high energy physics. Instead of using our accelerator for high energy physics, we use our other core capabilities. The big thing these days is looking for dark matter. People have figured out, or they're trying to figure out what dark matter and dark energy is. Nobody knows yet. So there's a big race in the world to figure this out. Figure the first person to discover it's going to get a Nobel Prize for sure. So of course we want to be involved. So there's a lot of projects going on. So instead of using accelerators and smashing particles to do this, a lot of what we do now is with satellites. This one shows a telescope. SLAC is one of the lead labs for building this new telescope, which is going to Chile. We're building the camera and operating it. So that's getting close to getting ready. There are a lot of underground detectors for detecting neutrinos and dark matter. We're involved in those experiments. So we're still doing a lot with high energy physics. It's just not our number one priority at the moment, but it's still very exciting for us. So there are a lot of core capabilities at the lab. It's drive what we do. So particle physics, which I mentioned, accelerator science and technology. So we're still one of the lead labs around the world for developing new particle accelerators. Large-scale user facilities. We have several large-scale facilities at our lab. A lot of advanced instrumentation and electronics for helping people do experiments. We have a lot of material science, chemical, molecular science, even plasma and fusion science. So those are our core capabilities. So we're expanding that a lot now to meet all the new needs, which I'll tell you about. Machine learning, of course, everybody does machine learning now, but it's very important for us. I'll show you about that. Visualization, big data analytics is also really important. All these telescopes and detectors produce huge amounts of data, and figuring out how to analyze it all is a huge challenge for us. We're doing more bioimaging. Of course, quantum computing, that's the latest thing everybody's onto, but of course we want to be involved in that too. So I'll tell you a little bit about these. So of course you've heard about big data science. You know, now you can get degrees in this. You can be a professional big data science person, which seems a little strange, but it's really important these days for a lot of activities. For science, what we're doing So one of our initiatives is single particle imaging. We're trying to use our X-ray laser and X-ray beams to image individual atoms as their motion and chemical reactions, biology, all sorts of things. But to do this, so you hit, I'll talk a little bit more about it later, but if you hit something with an X-ray beam, you try to determine what it's doing, just have incredible data rates, hundreds of thousands of gigabytes per second of data flowing through your detectors to analyze and to figure out these images. And just incredible computation power, like we use NERSC up at Berkeley for a lot of our computation. And so on the other scale, we have this large synoptic survey telescope, which I mentioned is getting built, and it's just about done. It's going down to Chile pretty soon. And so this has a huge camera. It's going to be running continuously. The data rates aren't so high, but it's going to have huge amounts of data, just because it's going to sit there and run for years and years and years, and have to analyze it, looking for new galaxies and dark matter. We do a lot of simulations for plasmas, particle beams. Again, it takes a lot of computation power. And all these we use machine learning, pattern recognition, other things which I'll talk about. So we have a lot of people working on this, trying to figure out how we can possibly manage all the data that's coming in from all of our scientific experiments. It's a little overwhelming at the moment trying to figure this out. So bioimaging is kind of a new thing for us. It's also big at Stanford, medical school, very interested in. So the new tool was developed not too long ago. Of course, electron microscopes have been around a long time. People have been using for forever. And just recently, people have come up with this new thing called a cryogenic electron microscope. And in fact, somebody got the Nobel Prize for it just a couple years ago. And it's like a standard electron microscope, but they have new detectors, and they figured out a way to cool biological samples down without destroying them so they can image them. And with these, you can get atomic resolution. So there's a lot of activity going on here. In fact, I think at SLAC we have at least 4 of these. We're going to have 7 pretty soon, and that's in conjunction with Stanford. And part of it's to have a facility on SLAC's site where people can come to learn how to use these machines and get training, and so they can go off and do their own experiments. And then we have another user facility where people can come and actually do experiments. And this really is part of this big data analytics thing. These things produce huge amounts of data, so much that you just can't sit there and do it yourself. You really have to have algorithms and figure out how to do that. But this is really a big thing for a lot of people because the resolution is so good. You can really figure out what's going on, looking for new drugs and structure development. So this is a new exciting development for us. So machine learning, well, of course, Silicon Valley, they developed a lot of machine learning. It's been pretty amazing, all the things they do. Pattern recognition, facial recognition. A lot of what they do is they go through thousands and thousands and millions of images looking for pictures of your dog, your cat, trying to find your friends where they are. So of course that's been a great success. What we do is more what we call scientific machine learning. So we're trying to use all the machine learning tools developed in Silicon Valley and adapt them for what we're trying to do is analyze science experiments. They use this a lot at the detectors at CERN where they're doing the Higgs boson. They have just huge amounts of data, and by analyzing millions of images, they can figure out what they're looking for, so they don't have to save all the data. They just pick out the ones they want, and then they can look at it more carefully. For us, we have all these facilities, which cost billions of dollars to build and operate, and we're trying to do it much more efficiently. I think we're going to be operating 4 major accelerators at the same time pretty soon. And of course, they never give us enough money to really staff up to do that. So we're trying to figure out how we can use machine learning to operate it more efficiently. We look at how operators operate the machine and turn that into algorithms to do that. And also similarly, we have a big machine that's very old, but still works. So we try to look at the data that exists and figure out how we can predict when things are going to fail so we can go and fix them before they break and cause us downtime. Because with facilities, our main job is to deliver x-rays to our users, so we don't want to have the machine off very long. Similar things with high-energy physics, like I mentioned. So there's a wide range of machine learning going on. And we recently opened up a new division to work on that for things across the lab. So a lot of excitement there. So quantum information science, it's kind of a new thing. People have been working on quantum computers, Google, MIT, IBM, lots of people have been working on this and have been a lot of neat advances. Nobody really knows what it means at the moment, so it's a great time to be in it because you can just make up stuff and get money. So it really is kind of a lot of fun. So at SLAC, we're not working on the computers themselves, but we're working more on the science that lies behind it. You have these qubits, what qubits are, can you make them better? So we're working on things like quantum sensors. This is a Josephson junction, kind of what's the basis of qubits at the moment. So we're working on improving those, developing new 2D materials, looking at for cold atoms and quantum states and how they interact. So one neat thing people did was take some of these sensors and they figured out they have such low noise, they're below the normal noise limits you have to deal with, and they're able to build this fairly cheap detector to detect dark matter. And so this is something we built a prototype of, and they're starting to scale it up and use that for dark matter detection over a very wide spectral range. So that's really a new thing for us, and it's very exciting, and we're working with Stanford and lots of other people, and also working with companies on that. Of course, batteries. Batteries are a big thing for everybody who wants to drive all these cool cars around. So we have an institute working on that. So it turns out for studying batteries, there's an electrode, there's usually a liquid, and what you want to look at is what happens at the interface between the cathodes and electrodes and the material and the liquid. And to do that, you have to have X-rays because you have to be able to penetrate through the liquid and see what's going on. So it's perfect for us. We have all these facilities to study that. So we have a lot of scientists coming. We get funding from the Department of Energy and companies, and they come and do experiments at our lab, trying to find better materials and see how to improve batteries in the future. So again, this is a great thing to work on. It involves material science, chemistry, electrochemistry, all sorts of interesting things. And then there are a few other things that are a little farther out. For example, we're trying to make really tiny accelerators. So our accelerator is 2 miles long. It's a little hard to carry around. So there's a group of people working on trying to make little tiny ones so you could produce an accelerator on a ship. That's what it's called. And one application is, so if you make it small enough, you could inject it into somebody's body for cancer therapy. So instead of shooting X-rays from the outside, which can be very damaging, you can put it inside and direct it right where the tumor is. We're also working on normal cancer therapy. We have much more modern accelerators, and there's some new techniques we're working on with a medical school where you can do cancer therapy much more rapidly and effectively without damaging tissue. And then lots of fun things with advanced instrumentation, working on neuroscience research. So that's kind of gives you an idea of all the different things the lab works on. I'm going to tell you a little bit more about accelerators. Joe and I here work in the accelerator division, so our job is to build and operate and come up with new accelerators for the future. But as I mentioned, we used to do high energy physics. At the moment, our concentration is on X-ray physics. So it turns out you can use electron beams and convert them to X-rays, which I'll tell you a little bit about more later. But anyway, what do you want to use X-rays for? Well, of course, imaging. First X-ray image was done in 1895, I believe. This isn't that one, that's a little newer. Turns out I worked at General Electric for about 10 years in the healthcare division. So I built X-ray tubes for quite a while, designed and built them. They're little tiny accelerators, they're about this big, but accelerators just the same. This is a device for doing cancer therapy. It's really an accelerator that turns electrons into X-rays. And every hospital has these now. It's made by Varian, which is also from Palo Alto. There's a lot done with using X-rays to study crystalline materials like DNA. So what you do is you run the X-rays through a crystal and it makes a diffraction pattern, and then you can turn that back into a structure and you can determine what DNA structures look like. It's pretty amazing. And other things, well, like for security, you want to look at what's inside trucks going through your ports and across borders, and you can use X-rays for that. These are all static things. So a lot of things people want to look at now is what changed over time. You want to look at a chemical reaction. You don't just want to see static things. Sort of as a fun side, well, stop action photography is really the basis for a lot of what you do for seeing how things change in time. So it turns out, of course, Palo Alto again started in the Bay Area. So Leland Stanford, who started Stanford, made a bet with this guy, Muybridge, and they were, at the time, nobody knew when horses went trotting down the road, do all their hooves leave the ground or not. So Stanford made a bet with him to see if he could figure out if that was true or not. So apparently it took him several years to figure out how to take all these stop-action photographs. and he finally won his bet. And this eventually turned into television, movies, and all that, so it started about that time. And this is really the same thing we do with X-rays. So again, what are X-rays good for? Well, time resolution is very important for what we're doing now. So you have to look at a wide range of time scales. The horse picture, that was taking a snapshot every second or maybe fractions of a second. Today, you really want to look at much finer time scales. So if you looked at technology, well, computers run at gigahertz rates. That's sort of nanosecond time scales. And maybe even faster when you're talking about transferring data, hundreds of gigabits per second, get up to picosecond time scales. If you look at nature, well, if you have a molecule, hydrogen can move along at sort of nanosecond time scales. Picoseconds, there are all sorts of things, spins processing in magnetic fields. That's what they use for MRI scans. If you get down to even smaller time scales, like light in 3 femtoseconds travels a micron, so that gives you a different time scale. And if you want to see what electron motion is, it's also about a femtosecond. It takes about a femtosecond for electrons to move around atoms. And so it turns out if you can make an X-ray beam with time scales in the femtosecond range, you can actually see electron motion. That's really what we're aiming for. And here's just an example of this is what biologists do. They're trying to figure out how DNA moves, how the reactions happen. And this is just a movie somebody made by taking snapshots in time with X-rays and then back calculating to figure out what the structure looked like. So this is really the goal of a lot of the things people do these days, trying to make molecular movies of chemical reactions, dynamics, batteries, all sorts of things. So it's really what the concentration is for a lot of things we do. So how do you make X-rays? Well, the simplest way is an X-ray tube. This is a tube you might when you go to the dentist and get your dental X-rays, there's a small thing like this. They're really pretty simple devices. You have a tungsten filament, just like it was in a light bulb years ago, and you run a current through it and heat it up, and the electrons just boil off. And you put a battery across it to accelerate the electrons across the gap, and they hit a material. And it turns out most of the energy just turns into heat, but some of it turns into X-rays, and those come out, and you can use those to expose an image. Again, there's just uncorrelated. It's not like a laser or anything. They just fill the whole space, and you put a film behind it and get your images. So what they do today isn't that different than they did back in the early 1900s. Again, the first X-ray tube was built, I think, in the early 1900s by some guys at General Electric. So if you fast forward to today, we have big machines to make X-rays. If you want to make very tiny very tiny X-rays, you need higher energy, so you need a much bigger machine. So this is called a synchrotron. This is at the SLAC site. This device has been here quite a while. It was also used for high-energy physics and got converted for X-rays. And these are really popular. There's a lot of these around the country, 3 or 4 or 5, maybe even more. And there's quite a few around the world, probably dozens of these. And each one can host thousands of experimenters per year. And these have been around for a while. We really know how to build them and make them very efficient. So these are quite popular. So how do they work? Well, it's a similar concept. You make an electron beam. In this case, you shoot it around in a circle. And whenever an electron gets bent on a radius, it emits photons. And so if you put your detector right here, you can do an experiment, and you can use the photons that come off there, or the X-rays, and do experiments. And so this one has, 30 or 40 beam lines around there, so you can do that many experiments at one time. And you can even make the X-ray beam a little better if you run it through this thing called a wiggler magnet. You wiggle the electrons around, and the photons and the X-rays all line up, and you get much more intense beams. So as I said, this is very popular. We have one here. There's one at Brookhaven in New York. There's one in Chicago. There's one at Berkeley, and lots around the country, around the world. So that's how things have been done up till about the past 10 years. So now the next generation of X-ray source is called a free electron laser. And the concept was invented in 1971. This guy, a professor at Stanford. And it took a while, really, for the technology to catch up with the ideas so you could make it much, much more efficient. But they were able to demonstrate that it worked. And the concept is pretty simple. Again, you start out with an electron source, just like in your X-ray tube. You have to accelerate the beam up to fairly high energies. You get a pulse of electrons. Then you run it through this thing called an undulator magnet. Magnets, the electrons come and wiggle around. And every time it wiggles, it produces photons. And if you make the spacing of the magnets just right, the electron beam energy is just right, all the photons add up coherently, and you get this laser-like pulse at the end. So this is really the first X-ray laser that's been built. You can do other wavelengths. You can make infrared free electron lasers. But for what most people want, you want to have X-rays. Because X-rays, if you have the right energy, they have a wavelength that matches most materials, like about an angstrom. And that gives you a good diffraction pattern. So most people want X-rays. So this was really the first free electron laser built. And you can adjust the temporal spatial resolution by adjusting the size and energy of the electron beam and the duration. And so this just shows one pulse, but in fact you have multiple pulses coming with some defined spacing, and you use it like a strobe light. And this is really how they make molecular movies. They just run this laser, you get a pulse, measure something in your detector, either change your sample or look at it again a short time later and make up a whole pattern, just like the horse picture I showed earlier. Then you can send it to your favorite chemist or biologist, and they turn it back into what real structures look like. So there's really a huge amount of things involved in here. Lots of technology and the science end and data analysis. So it's quite a complicated system, but produces just amazing results. So there's a lot of activity going on in this area now. Again, free electron lasers are getting built around the world. Turns out the first one, called the LINAC Coherent Light Source, was built at SLAC about 10 years ago. The idea was conceived by this professor at UCLA, Claudio Pellegrini, who now is retired, but he works at SLAC most of the time. So what we did, well, we were looking for something to do with the accelerator. So we said, well, why don't we just use part of the accelerator? We accelerate the beam from the injector, make an electron, gets accelerated at very high energy. LINAC means linear accelerator. You go through this wiggler magnet, or undulator magnet, to make the X-rays, and then you put user stations down here. So this is still a very large-scale facility. I remind you, it's about 2 miles from there to there. And so it's quite a big device. So this has been running for 10 years now, and the anniversary party is April 10th, if anybody wants to come. So we had a lot of great science done, and it's really fun because it's all new. It took people quite a while to really learn how to use it. The normal X-rays I showed you from before that people use, you can put a sample in there and expose it for a long time and get good results. But these beams are so powerful, when you hit the sample with a pulse, it destroys the sample. So you have to have your detectors fast enough to capture the data before the sample explodes. And there's a whole industry basically trying to figure out how to make millions of samples and shoot them through the beam and capture them while they explode and get the data. So it's all pretty neat. So there's a lot of new things going on, a lot of new technologies. But really the science is very new, and all things people can do are pretty amazing. So if you look inside of this, so this is the undulator line. So this is the magnets that we had to build. So these have lots of little tiny magnets in there and make the beam wiggle around. This whole device is something like 100 meters long. So this is really large-scale science. And everything has to be very precise. Electron beams are a few microns in size. And these magnets have to be aligned perfectly to it. You can see motors on all the stages. So you have to shoot the beam through and you align the magnet so it lines up perfectly with it. So there's really a lot of science and technology and engineering goes into making these things work. The whole room has to be temperature controlled to keep things stable. So anyways, there's lots of things people have found. So we look at ultra-fast science. People are trying to use this to study charge dynamics on a very fast scale, figuring out electronic structure, how chemical reactions happen. Trying to take movies, like I mentioned. A big thing people do is trying to figure out how photosynthesis works. Imagine after all this time, people have figured it out. There's a very complicated cycle, and it has very different time scales as you go around this cycle. And they figured out a lot of it, but the last few pieces, you really need femtosecond time resolution. And we're just getting to the point now where they can start to figure out the dynamics in that part. So that's a very exciting thing that's going on. And with the machine I'll describe in a minute, you get much higher repetition rates, and you can capture things much faster. And studying quantum materials, you need much higher resolutions. The new lasers have much better properties, and you can study things on very fine time scales and resolution, trying to figure out what's going on at new regimes. So anyway, what's next for SLAC? So we've had this accelerator running since 1962. Surprisingly, it's still running very well. Turns out most accelerators in the past were made out of copper. So have these long copper structures. They have little cavities inside called resonant cavities. So if you put microwave power into it, just the right frequency, it's very similar to a microwave oven that makes the power to warm up your food. The power comes out of a microwave and goes into the structure. And these cavities capture it long enough and hold it, so when the electron beam goes through, the power from the microwaves gets transferred to the electron beam and accelerates it. And this is really what a structure looks like. And again, the original machine was built at SLAC a long time ago, and it's 2 miles long and makes many billions of electron volts worth of energy. But these really are limited in how fast you can pulse them and the average power they can handle. Just because copper gets hot, a lot of the energy goes into just heating up the copper and heating up water. So it's not very efficient, and you just can't run it very high or the thing will melt. So what we're doing now, we're building a whole new accelerator, a new free electron laser using superconducting accelerating technology. So we're replacing these copper cavities with cavities made out of niobium. So it turns out when you cool these things down to liquid helium temperature, below 4 degrees Kelvin, they become superconducting. So that means you can put a lot more power into them. You don't have to worry about heating. Superconducting means there's no resistance to the flow of electricity. So you can run much higher repetition rates, much higher average powers. And that gains us a lot of things. With high average power and high repetition rate, we can do many more experiments. The copper LINAC, you basically shoot the beam and you do 1 experiment or 2 experiments at a time. With this one, with a high repetition rate, we can easily split the beam up into a dozen different experiments and have much more throughput. And part of it's because it's been so successful, we have way more people wanting to use our machine than we have time available. I think with all the proposals come in, maybe we can fund 10% of what comes in per year. So we really need to expand our capacity. And so this is one way to do it. And so this has been a very interesting project that's going on right now. So this is a picture of the whole machine we're building. Again, this is the beginning where there's an electron source back here. So we have a whole kilometer of these superconducting cavities that we're building. There's a huge cryogenic cooling plant, which I'll show you in a minute, that we're building. Then the electron beam gets shot down through a long tube, through these undulator magnets, and down to user stations. So this only fills up the first third of the LINAC. At the back third, this is the original copper machine that we built years ago. We're still using that, so we'll have multiple accelerators running at once, feeding X-rays to our users. So this is going on right now as we speak. Just a few of the parts that are inside. So this is what we call a cryomodule. Inside here are 8 of these superconducting cavities. This whole thing is about 10 meters long, and we stack up 40 of them one after another to give us about a half a kilometer or close to a kilometer of space by the time it's all built. It's been an interesting project. In the old days, when you had national labs, like you'd have a project, do everything yourself. It's the original SLAC accelerator. They built the cavities, they built the power tubes. Everything was done on site. These days, it's a little hard to do. I mean, we would like to do that, but hiring all the people to come to SLAC to build all this stuff just isn't feasible these days. So we worked with partner labs. This one shows Fermilab in Chicago. They built half of these cryomodules. Another lab in Virginia built the other half. Somebody else is helping design and build the cryo plant. SLAC, we did all the design, integration, testing, and then we'll operate it. So it's really a nationwide effort to get all this done. And we even use vendors in Germany to build some of these cavities. So it's really quite an effort to get all this done. So if you're interested in project management, this is quite a place for them, because just dealing with so many different people and vendors around the world, it's a huge coordination challenge. So these are shown in our tunnel. We're installing them right now. Things are a little behind as usual, but we're catching up. This shows another picture. This is a cryomodule in the tunnel. This is a big tube where the liquid helium comes in from outside. These pipes here, this is where the power goes into the cryomodule. This is in the tunnel. It's about 30 feet underground. We have to have everything underground. It makes a lot of radiation, so for safety reasons, it has to be underneath a lot of earth. But the microwave tubes are up above, and the power comes down here and feed into the cavity. So again, it's quite a complicated device. And hopefully you guys can come for a tour sometime and see it all in action. It's pretty fun. So the other big thing is a cryogenics plant. So to cool this whole thing, you have to fill the entire thing with liquid helium. This is a big industrial plant that we're building now. It's actually almost complete. Like I said, the cavities are made of niobium, and you have to make liquid helium, you immerse it in liquid helium, it becomes superconducting. And so you can see here's the cavities themselves, and there's a whole big distribution system. So this is what the inside of the plant looks like. It's really a sophisticated industrial system, and there's all sorts of things you have to take. You buy helium, big helium tanks, like you get for your balloons, just much bigger. And this plant converts that from gas at room temperature to liquid all the way down to 2 degrees Kelvin, or 2 degrees above absolute zero. So this is quite a sophisticated plant and lots of components. So again, if you're into plumbing and systems engineering, this is quite a fun thing to work on. Just to give you an idea of the scale of some of these things. So this is inside the plant, these huge cold boxes for compressing the gas. Those are more cold boxes outside the system. And so we're very close to having this whole thing complete. Maybe this summer we'll start turning it on and commissioning it. So anyway, what's next? So we're installing this right now. We're in the middle of commissioning, installing, or in the middle of installing and getting it built. We're planning on being able to serve thousands more users than we are now. And we're really hoping this machine will keep running for another 50 years and keep us all employed and happy. So what can you guys do to help? There's a lot of excitement going on. There's a lot of things going on at Stanford. I know Silicon Valley, it's all you ever hear about, Silicon Valley stuff. Making lots of money, which is good. But if you're really into science and engineering, we do a lot of really high-tech things, a lot of things you may not hear about a lot. But we need people of a huge variety of skills. Just by my presentation, you can see all the different things we do. We're a wide variety of scientists. We have physicists, chemists, biologists, you name it, data scientists, computer scientists, engineers from every field, electrical, mechanical, civil, you name it, we've got it, environmental. Do a lot with operations. We have these sophisticated plants. We have to keep them running 24 hours a day, all year long. So we have a big operations staff. And then, of course, HR, business, finance, all those things. Project management, like I mentioned, safety. So pretty much every skill you can imagine we need. So if you want to learn more, well, at SLAC we have internship opportunities for undergraduate students, high school students, even teachers. There's some teacher programs. Lots of summer programs we have for all ranges of people. We host graduate students from Stanford, from all sorts of different schools. I have a graduate student from Santa Cruz right now. Over the whole lab, I know we have several hundred grad students probably. So if you're thinking about grad school and you don't have to go to Stanford to work on your graduate degree, you can work at a different school and come, again, work on any end of the accelerator, or experiments, batteries, all sorts of fun things. And like I mentioned, we're hiring at all levels, PhDs, masters, people right out of school, welders, you name it. We need absolutely everything. As Joe will let you know, we have a struggle finding enough people to do all the work we've got, which is a little frustrating. We're getting lots of money, lots of exciting science, but it's really a challenge finding the people we need to get to the next step. So anyway, thanks for having me here today. Just a nice picture of the whole machine. So if anybody wants to come out for a tour, we have public tours quite often, and we're glad to have visitors. So any questions?
Let's thank the speaker. And this group usually has questions, lots of questions. So if you do have one, please raise your hand.
Yeah, anything at all.
And we'll bring a mic.
So with the machine like 30 feet down underground, how do you handle earthquakes?
That's a good question. We have, well, there was one, when was the last one, in the 80s? I think there was some damage from that. So we have to go to a lot of extra effort to make sure all the equipment is anchored, everything is secure. A lot of analysis goes into how to handle that. Yeah, I used to live on the East Coast and build accelerators. Yeah, we didn't worry about that much. But here there's a whole extra level of scrutiny, especially. So we have a whole engineering group which studies that and makes sure everything is solid and can handle that. But of course, if there's a big one, the accelerator could get damaged. So it is a big concern for us, for sure. Good question, though.
What fraction of the world's helium production do you use at the lab?
Oh, that's a very good question. Turns out to be a big problem at the moment. The U.S. used to have a huge helium reserve left over from World War II, I think, when they wanted to fill up their helium balloons. And they decided they don't need it anymore, so they've been selling it off. And it turns out that superconducting cavity technology has really blossomed, and there's a lot of this around the world. The Accelerator at CERN, they don't have superconducting cavities, but they have superconducting magnets, so they use a huge amount of helium there. And at the moment, we're working on getting contracts to get enough helium to cool our accelerator down the first time. So it's a big challenge, and you really have to plan ahead these days. And in the old days, people would just, when they were done with stuff, they'd just open the valve and blow it off into the air. Because there was so much nobody cared. But now you can't do that. So pretty much everybody is working on getting a helium recovery system. So when the helium vents, for whatever reason, you have to try to recover as much as possible. And that's a struggle too, because the accelerator is pretty big, and at the moment we don't have enough storage tanks to store all the helium. So if we had a power outage, say, and the helium warms up, we can't even capture it all. So it's really a national and worldwide issue at the moment for all of us. So there's a lot of concern about that. If you got any good ideas, let us know. Don't buy any more helium balloons. So.
I forgot my question. So SLAC obviously did a lot of important science for its time and all the discoveries of the quarks and the like, but became obsolete as other, if you'll excuse the term, other larger accelerators were made. Is there a corollary with that, with the ultra-fast X-rays that you're doing now, or will SLAC remain as one of the best or the best in that regard?
Well, that's our mission for the DOE is to be the world leader in ultra-fast X-ray science. That's our #1 goal. But there is a huge amount of competition. After the success of the machine we built 10 years ago, these things are popping up all over the world. China, Taiwan, Germany just built one very similar to the one we're building. There's a lot of competition, so we're ahead of the game now, but yeah, it's hard to stay in. But the DOE, Department of Energy, wants us to stay ahead, and they're pumping in a lot of money into this, a lot of the money into the science. You know, it's really about the science. It's not about this accelerator technology. It's about what science can you do. So that's really where the focus is putting enough money into science to advance our future, biology, chemistry, all these cool things that are going on. So they really are putting a lot of effort into it and want to make sure we stay ahead. So it's a great place to work. We have lots of money, so we have trouble spending it because we can't find enough people, which is why I'm here today.
Other questions?
Must be a few more.
Okay, well, I have one.
Okay.
Well, and then we have one more over there. So if you're in the business of trying to do science, and then we're sitting in Silicon Valley, where I think it's easy to measure the value of all the products because things get sold. That paper in Nature doesn't really get sold. So in the end, I guess what are the metrics that you are using when you go and argue to DOE for more money? Because these are things that are, ideally they're 20-year time horizon things. Really
Yeah, it is a challenge. Yeah, we don't have the immediate payback for things. But a big one is publications in important journals. Like they see how many Nature papers our scientists produce, and then they figure out how much money they spent on it, and they try to get, how many dollars per publication. So that's one metric that's important to them. But yeah, obviously coming up with things that have big impact, battery technology. If you could figure out how photosynthesis works and you could make artificial plants, that's things like that are really the big push, is trying to figure out how to make us energy independent and come up with new technologies. So yeah, it's hard to measure. So when you go and think about all Silicon Valley companies and what they produce and all the money they make, it's a little hard to compare. That's probably why you don't hear about SLAC so much, because there's so many other things going on at the same time. SLAC without a K, yeah.
Hello. So earlier you mentioned something to the effect of scientists are leaving the United States. Why is that occurring?
High energy physics, that's probably what I meant, is a lot of the U.S. used to be the leader in high energy physics, and a lot of that's changed over the years. Why has it changed? I don't know. I think part of it's emphasis changed, and then they built these big accelerators in Europe, and they sort of took over. And there was a time where the government didn't fund things. There was a big accelerator they were going to build in Texas back in the 90s, and it got started, and that would have been the similar scale as the one in Switzerland, but it was way over budget and got canceled. And that really was sort of a death blow for high energy physics in the US. So they've never really recovered from that. So a lot of the high energy physics machines are in Europe. A lot of the high energy physicists people are still in the US. They do science. They just have to travel there to do their experiments. So it's changed quite a bit, but a lot of it's just because of that machine that got canceled in the 90s really put us back. So things have changed quite a bit, but we're working more on like satellites, telescopes, different ways to do things. And Fermilab still is a high energy physics lab. They have a big program now where they're turning in a neutrino lab where they use an accelerator to generate neutrinos. Then there's an underground detector in South Dakota. So they shoot the neutrinos through the Earth, and the detector is 800 miles away. So that's a really big project that's going on now in the Department of Energy. So we're still doing some things, just emphasis has changed some. We're trying not to lose leadership in X-ray science. So that's
All right, I've got one more question, and keep thinking of more questions out there. What are the challenges in management of I've heard you talk about Nobel Prize winners and welders, and maybe not in the same sentence, but you can imagine that you've really got people with very diverse backgrounds working on some of these projects to do the science and then to build the infrastructure to do the science. And what are the management challenges associated with that?
Oh, well, boy, yeah, there's a lot, yeah. So a lot of it's probably communication, and the scientists come up with all these great ideas, and after you're working on a big project, and they figure out all that, and the technician is just given jobs to do. And so I think a lot of it is communicating why it's important and why people are doing these jobs. Yeah, sometimes they just get lost, and they probably don't understand why they're there. So a lot of them come to work at SLAC because they're interested in the science, and if they don't get that feedback and support, I think that's a problem. So it makes it hard to keep people if they aren't engaged. So I think communications is really the hardest part across such a wide, people with PhDs and people who work in the machine shop. It's just a huge range of skills and knowledge, and trying to keep everybody involved and excited is probably the biggest challenge. So we have a big communications department to keep that going.
All right, great. I know there was a hand up on this side of the room. Okay, great.
Hello. Can you tell a little bit more about the internship programs available for undergrads?
Yeah, so we have a number of them. We have one person at SLAC who runs the overall internship program. I just saw a presentation by him the other day. So let's see, which ones were there? There's a wide variety. There's a lot in the summer. There's something called a SULI program, which is run by the Department of Energy. Any undergraduate can apply for it, and it's to work at a national lab. I think we have 30 or 40 interns, usually per summer, in a wide variety of fields. That's a good one. We don't have to pay for it. The DOE pays for it, and you get paid stipends for that. That covers a wide range. We have ones for teachers who have, like professors who want to come with grad students. There's ones for that. Joe, who's in our electrical engineering department, he's interested in getting people just for that field. That's one thing we want to talk about today. Our mechanical engineering department recently started their own internal program for interns. We have at least one student from San Jose State. They're trying to get students from local colleges. And those are three that I can think of. I think there's a few more. But we have a list I can send. But yeah, we'd love to get more people involved, especially local people. Again, our biggest problem, hiring people, it's hard for people to move here for a short time. So if we can find interested students in the area, it makes it a lot easier. So we're focused on people nearby who don't have to relocate. But yeah, we can provide a list. That would be a good thing.
We'll make sure that gets in your newsletter, so make sure you read your student newsletter.
Yep.
All right, any last questions? No, there was a hand up on this side. maybe the question was about internships. All right, I think with that, let's thank the speaker again. And if you all are taking part in the Engineering Go program, this is a Go Point event. So just again, a picture of yourself in the vague vicinity of this room with these wonderfully colored walls will count. And that slide would be perfect, the summary slide. So thank you very much.